Any questions from anyone? Okay, so like I said last time, I want to spend the bulk of today mostly just having a group discussion kicking around project ideas. Before I do that, there were just a couple of things that I wanted to mention as people get started with Lab 3. Because a few groups have gotten started with Lab 3, and there have been a couple of clarifications that I've needed to make to every group, so I thought I'd just make it to everyone here. So I'm just going to share my screen and point out a couple of things. The first is what Bruce was just mentioning a little bit, which is on the Lab 3 write-up. I point you to, let me see, where am I going? As a place to start, I point you to example 4 on this PIC32 DSP page, which includes an implementation of the FFT algorithm that's written out at the farther up on that web page. I just want to point out a couple things about this example. Oops, that's not the link I wanted. So what I wanted to point out is this lab is, there are a couple of different examples that you will have to start with and combine, and each one has a particular thing that is of relevance, and the rest of it is less relevant. So the thing of relevance in this example really is the implementation of that FFT function. So you can see how that works in this example. Keep in mind that in this example, the fixed point data type that's being used is one that's created in this file called fix14. You can use that if you want. I would probably recommend using the accum data type that we used in the previous lab, and the version of the function that's written at the top of the Lab 3 webpage is written using that accum data type. So I want to just point you to that. That is the thing to pay attention to in this example. If you fire up this example and you start trying to talk into it to see the FFT dance, you're probably not going to see anything. And the reason for that is the analog to digital converter sampling in this example is at 500 kilohertz, which means that you are observing frequencies in that FFT up to 250 kilohertz. And you'll remember from a couple of lectures ago that our voices are somewhere in the hundreds of hertz range, maybe up to a kilohertz, which means all the information from your voice as you talk is in the bottommost pixel of that FFT, and you're not going to be able to see anything that's going on. The other thing just to notice about this example is it uses DMA to sample the analog to digital converter. You do not have to do that. So if you want, the place to go look for how to set up the analog to digital converter to sample in your software, as opposed to using DMA, I'll just show you here, is on the analog to digital converter webpage. The first set of examples here. This example code sets up the ADC and then reads it in a thread. You'll be reading it not in a thread, but in an interrupt service routine, but the code looks the same. So you can find the setup code for the ADC here. And like I said, we'll talk through this on Friday. We didn't get to this on Monday. We'll talk through this on Friday, but you can see how to set up the ADC here. And then the thread that reads it is shown here. And really the two lines of interest are just these two, where we call read ADC 10.0. This is, we'll see this on Friday, but the ADC stores its outputs into a buffer, and we're reading the 0th element of that buffer and storing it in a variable called ADC9. And then we call the plib function acquire ADC 10, which starts a new ADC acquisition. And we're doing this after we do the read so that it starts doing the work to acquire that next ADC sample while we do other stuff. And by the time we get back here to read it again, it's ready for us. So it's in this order just to avoid an unnecessary wait. Okay. So the point that I'm making is just that for setting up and reading the ADC in software, please look at these examples. And then for seeing how to use that FFT function, please see the other example that's linked in the Lab 3 write-up. Okay. Any questions about that? You'll notice in general, these lab write-ups are getting a little bit, what's the word, shorter or something. And the reason this is intentional, we're sort of giving you a slightly less every lab, with the idea being that you're developing comfort with this material and you're developing the skill to go dig through data sheets and figure some of this stuff out on your own. So it's intentional that it's sort of the examples from which you start are a little less complete, or they're a little more scattered. In this case, it's sort of in 2 different files. In the next lab, it'll be even less. And then that's leading you, of course, towards the final project where it's totally up to you. And there are lots of examples on the webpage to start from, but it's up to you to sort of piece them together. So that's why, that's intentional. We're just reassuring you of that. Any lab 3 questions as people have been getting started? The other thing about lab 3 is, like I mentioned last time, I will move your scope probe to the analog input. So right now, both your scope probes are on the DAC outputs. I will move one of them to the analog input whenever you would like me to. Like I said last time, I don't want to do that before you ask me, because you might be using that to gather information for a lab report or something. So just let me know when you're ready and I'll move that scope probe, and then you'll be able to fire up the oscilloscope software, talk to your PIC like I was, and see your voice waveforms dancing. Start sampling them. Okay? Questions right now? At lab 3? Okay. In that case, what I want to do for the rest of today is basically just have a group discussion where we kick around project ideas. And I've started by just coming up with a few general categories of projects that I could think of some potential. I could think of projects that fit into each of these categories. There are more categories that we can add to this list. And then I thought as a group, we could add some projects to this list and talk through them. So to that end, I can just get started. And then as people want to contribute what they've been thinking, just please do. I thought that we would start because we've been talking, our labs have been kind of audio centric. And we've been talking about a lot of audio projects. So I thought we would maybe start by talking about some project options that are not in the audio category and just save those maybe for the end, because if people are more interested in something like computer graphics or something like this, I want to talk through some options that exist there. So with respect to computer graphics, I'm going to be looking over my right shoulder because I have stuff written on my whiteboard. So let me just get started here. A category of computer graphics, I guess you could call this a computer graphics problem. It's also kind of an algorithms problem, is cellular automata. People know about this? So these are fun projects. The most famous example of a cellular automata, I think, is Conway's Game of Life, which you've probably all seen. I also learned this morning when I Googled this that this is one of those, Google has one of those little things it does where when you Google it, it does something. So what you can see on the Google page here is it's starting to run Conway's Game of Life coming in from the 2 sides. Conway's Game of Life is a cellular automata. What that means is the screen is, let me stop this so I can open the Wikipedia page. The screen is divided into a bunch of rectilinear cells, essentially divided up into square cells. And those cells are either colored black or they're colored white. And as time progresses, their colorization changes based on the colorization of their nearest neighbors. And I don't remember exactly, well, all the rules are written here. So let's see. Each can only see its 8 neighbors, which are the horizontal, vertical, and diagonally adjacent neighbors. And the rules that each one follows between time updates is any live cell, which is one to say that that is whatever color you're using to represent alive versus dead. So any cell that is the alive color with fewer than 2 live neighbors dies, kind of simulating an underpopulation problem. 2 or 3 live neighbors lives to the next generation. More than 3 live neighbors dies, as if by overpopulation. And then a dead cell with exactly 3 live neighbors comes alive, changes its color, and switches to the color that you're using to signify life, kind of simulating something like reproduction. And when you run this, so you can set up the grid with, you could start it with a user specified initial condition. There's some special initial conditions that lead to some special results, or you could just randomly populate the screen with cells that are on and off and click run. And what ends up happening is these kind of fascinating patterns develop and start moving across the screen. And this has been studied enough that a lot of these patterns now have names. So for example, this initial configuration sets up a structure that generates what they call things that move across the screen, they call spaceships. So it generates these spaceships. This is called a glider gun, generates these things. You can set up other things that cancel each other out. In fact, it has been shown that Conway's game of life is Turing complete, which means you can set up an arrangement of cells to do any computation that a computer can do. And there's one, I mean this in the the nicest way possible. This one psycho that I found, he figured out how to build a full CPU, a full processor in Conway's game of life. If you Google this, you'll be able to find it. It's absolutely amazing. It's such a cool thing. But in any case, it's a very interesting sandbox to play with.
Did this while he was a astrophysics PhD student. One wonders what his advisor thought about it.
But it's very cool. So this is by far, I would say, the most famous example of a cellular automaton. There are other examples of cellular automata that you might also implement. So that's an example of a sort of computer graphics-y problem. Other ones are particle systems. These are kind of fun. Let's see, I have an example. Let me see here. So particle systems. So what a particle system is kind of like the Boyd's lab. You have a bunch of individual particles, colorized pixels or circles or whatever they may be. And each one is following a specific set of rules, often associated with where it is on the screen. In these systems, it's less common to have them see the other particles. More often, they're totally independent entities that are each following the same set of rules based on their position on the screen. But you can play with the rules that they follow based on their position and create animations of stuff that, in this case, this kind of looks like water filling up some sort of a vessel. And when it gets to the top, it overflows. That's one particular set of rules that creates sort of watery looking graphics. A different set of rules creates something that I think looks kind of like fire. With a different set of rules, you can create behavior that looks like smoke. So you can create these particle systems that, as you tune them, end up looking quite natural. So you can create flowing water, flames, smoke, wind, snow, rain, all this kind of stuff. So the artistically minded among you, you could do something kind of fun like draw a scene on the TFT display, maybe mountains and a river and a little house with smoke coming out of the chimney, and you could use particle systems to actually create flowing water and billowing smoke and all that stuff. That might be kind of interesting. I find those quite fun, and you can transition from one particle system to another particle system quite easily because it ends up being essentially a modification of a few parameters or a few rules. So the part of the code that you actually end up modifying to create a system of totally different behavior ends up being pretty small. So once you've got something working, it's a thing that's very fun to play with, which is nice in projects, I think. Let's see, I'm gonna add, this kind of couples with what I just mentioned, but any kind of like dynamic or procedural art. So drawing designs on the screen based on some set of rules and having that evolve over time. That's kind of loosey-goosey sort of, I don't really know what I'm talking about there, but something in that general flavor of just, it is a shockingly difficult challenge. If the challenge that you choose to accept for your final project is, I am going to make something that is pleasant to look at, something artistic that is pleasant to look at. That's a shockingly hard challenge. So that's appropriate for a final project. Something that's pleasant and interesting to look at is something that's going to change over time, something that looks right in some difficult to really specify sense, right? So that's a hard challenge. And if the artistic among you wanted to accept that challenge, that would be okay. You could do fractal landscape generation. We had a group in 5760 do this with a lot of success. There are algorithms by which you randomly and fractally generate landscapes, by which I mean you start with some flat plane, and there are rules by which you change the elevation of areas of that plane, starting with big changes and then getting smaller and smaller and smaller. And the overall consequence is that you can generate landscapes that look shockingly real. This is the strategy that's used by a lot of video games to generate mountainscapes and that sort of thing. Changing parameters, you move from mountainscapes to something that looks maybe something that goes from the Rockies to something like the Appalachians, perhaps. And then if you wanted to get into some real computer graphics sort of problems, you could try to render the landscapes that you generate in something like 3D and get the shading right. That's a hard problem, but that would be a very appropriate problem, I think, for a final project. You do L systems. This is another one that's kind of on the boundary between computer graphics and algorithms. L systems are, oh boy, can I describe these in a way that makes any? So L systems are, you start with some string of characters. Each of those characters means something. So maybe a particular character means move forward. Another character means turn right by this amount. Another one means turn left by this amount. So you go through and you build up a path by following the rules specified by the characters. And these things evolve in that there are rules by which from generation to generation, a particular character turns into new characters. So you start with a short string, and then you evolve that string where you build up more and more characters following the rules for that particular L system, and you end up with quite a long string, which draws a complex structure. And depending on the rules that you follow, you can generate some really interesting looking things. Let's see, if I Google L systems, do I get pretty pictures? I hope so. So you can generate very plant-like looking things. Okay, so these are all procedurally generated L systems. Some kind of look like ferns, some look a little more twiggy. Changing the rules slightly changes how these plants evolve and how they look. This would be a very interesting project. You can use similar rules to generate familiar structures like the Sierpinski triangle, generate dragon curves. People know what the dragon curve is? Dragon. These fractal shapes. You start with a simple set of rules, evolve, 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 build up more and more complex structures, and you end up with these sorts of shapes, which are very pretty. They're nice to look at. The dragon curve is also famous because, for those of you that are fans of Jurassic Park, like I am, the dragon curve is featured prominently in that book. It starts each chapter. You start with generation 0 of the dragon curve, which is basically 3 lines. And then as the book progresses, the dragon curve evolves into these sorts of structures, supposing to represent the chaos is a theme in that book, and it's supposed to represent chaotic formation. So those could be interesting.
Hey, Hunter.
Yeah.
To what extent are we allowed to use Python as well? Because I know there's some like higher level libraries in Python that I'm sort of interested in using, but I understand we have to use some of the PIC32 functions as well.
So that's a good question.
You mean Python running on the PC?
Yes.
And then communicating with the PIC through that UART connection that we've been using or something like
Yeah,
it.
something like that.
So generally speaking, I would say projects that do that are totally fair game. There has to be sufficient use of the PIC32 where sufficient is a difficult to quantify thing. If you were to write up a project proposal that proposed to do something like this, and we could look at it and see, and you could articulate, I'm going to do this in Python and this on the PIC32. I think we could give a per project feedback on that sort of thing. But generally speaking, if you wanted to do some computation or some work in Python and then do some rendering and real-time stuff on the PIC32, I think that would be a wonderful flavor of project.
Okay.
Yeah. This is everything I have on my whiteboard in the approximately computer graphics category. Has anyone else been thinking of projects approximately in this category that I could add to this list?
I do have something, but it's mostly computation on the system and then just rendering on PIC32. So I guess it doesn't stand because PIC32 will only be used to draw on on the TFT screen, nothing else.
I would say it depends how complicated that drawing is. If you're doing like rendering and shading and that sort of thing, that's a sufficiently complicated render process. If the PIC32 is only being used to essentially deposit information into pixels that's coming from Python, that might be not so good as a final project for this course.
Yeah, so I'll have to think about it, but I do have something in mind.
Okay.
It's called messy curve draw. Like it's another category of generative art.
I've not heard of that. Sounds interesting. Okay.
Yeah, I mean, if there's a YouTube channel called the dot is black, and he has done some interesting stuff with that. He doesn't share his code, but only the work he does.
Okay.
So
Okay.
like he has drawn some really interesting art and stuff. So that might work.
Cool. Okay. Okay. I'll look that up. That sounds interesting.
I got throw one other thing on there, I guess, would be visualization of nonlinear systems, like Lorenz oscillators.
Something else that I was thinking of in sort of the graphics world, I think it would be pretty cool to try and implement like a finite element calculation and then show the results on the TFT display. So show, exaggerated deformation of something under compression or something like that.
David,
So in that case, would you be doing a 3D rendering then on the PIC32?
Probably not, probably just two-dimensional.
So again, it seems like it's got to do more than just grunt pixels onto the screen, right? If you send an object description to the PIC32, which is then rendered from the object to the pixels, I could buy that, I guess.
Okay.
That'd be cool. And you could start, of course, with super simple things, a cube, just like a perfect cube, and do some FEA on that and see if you can get that rendered and then add complexity. Yeah. Kat, did you have something? Oops. Okay, I'm not sure if you're talking, but I can't hear you.
I keep turning my headphones on and off and they're being weird. Can you hear me?
Yeah, I can hear you.
Okay. I have an idea, which is inspired by Grace making fun of her failed Boyd simulation. Because when they were not behaving flock-like, she joked and she was like, it kind of just looks like one of those ideal gas boxes. And what I thought might be cool is to have a very simplified simulation of comparing an ideal gas versus a van der Waals gas. I'm sure van der Waals gas simulators exist. I just don't think I've ever seen one. where maybe the Python GUI lets you select different gases that you want to have. And like the ideal gas rules are simple. They don't have volume or attraction, and for van der Waals gas they do. And then to account for, like, I'm obviously not going to run actual quantum simulations on the PIC, but maybe just have some kind of matching and repulsion factor based on the actual gas constants associated with the element that you select, and just have this variable stored.
I think that sounds like a great idea. So it sounds to me like you're essentially, this would sort of amount to changing, because the gases do see the other gas particles, as far as I understand.
For van der
So
Waals, not ideal.
For
Well,
van der
for
Waals,
ideal-
it's not ideal. Okay.
For ideal gases, though, they do collide. It's hardball collision, but they
Yes.
do collide.
Yes.
And so you have to get, and then for van der Waals, you could use a Leonard Jones potential.
Yes, exactly.
I think that's a great idea. I think that'd be very cool.
Thank you.
Okay. So another fun category of projects that tends to be popular is games of various varieties. Games make nice projects because, well, all these categories make nice projects. One of the nice things about games as projects is there's a lot of instant gratification associated with optimization. So it's very self-motivating to optimize games because you're playing with it. And as you optimize, the playing experience tends to get better. So it's nice because it really, it makes you really think, whether you like to or not, about a lot of the optimization techniques that we've talked about in this class. So games that make sense on the PIC32 is almost any of the old school classic arcade games. So things like Asteroids, or the Brick Breaker games, or what else do I have written down here? Tetris. You could likely implement on the PIC32. Asteroids.
I saw a group once who figured out how to do a cheap rendering of a 3D maze. So it's first-person shooter in a maze that was 3D. You saw the walls go by you, but it was no 3D calculation. It was all 2D tricks with polygons. And it was running on an 8-bit microcontroller with accelerometer sensing in real time. So I know it would run a PIC32. Now then the question asked, if you had a friend who was sitting at the next computer, could you make a 2-person game where you had 2 or more PICs hooked together, each with their own display, so you saw your version of the maze, but not the other guys?
2-player games. That could be cool. I hesitate to even say it, but could you get Doom running on this thing? I don't know. People have gotten it to run on some crazy things. So the particularly computer sciencey among you, do not undertake that challenge lightly. But if you were interested, you could try to see if you could get Doom up and running. Any other games? Any other games that people have been thinking about?
Shreyas and I were throwing around the idea, but now it just sounds too simple now that you have mentioned all of these. We were trying to, implement Google Dino game, and as an input, instead of using buttons, we'll just whistle.
I don't think that's too simple. I think that could be a very well scoped project. So the Google Dino game being the game that pops up in the browser when you don't have an internet connection.
Yep.
Okay. Google Dino, the Dino game, voice controlled. I think that's a good idea. Make sure Zoom doesn't filter your whistles too much. Might be the only concern with that.
Yeah, we'll hard code the values of our whistle frequency.
Okay. So with respect to physics, we've talked about some of these, so I'm just going to put some of the stuff that might loosely fit into this category that we've already discussed here as well. So we could do gas simulations, we've sort of discussed. Maybe that's the only thing that approximately fits in this category so far. You might also consider doing, you could do gravitational sorts of simulations. N-body problem stuff. You could have a bunch of stuff orbiting around one another. See how many you could get in real time. There's a lot of inverse squares there. There are some tricks for doing that quickly. So it's a good opportunity to deploy some pretty cool tricks from the computer graphics community. That weird floating point square root, right, that Quake famously used. Deploy that and build some pretty serious gravitational simulators. A gravitationally based video game might be kind of interesting. Some sort of game that uses gravitational dynamics could be kind of cool. I'm thinking like some sort of very scaled down version of something like Kerbal Space Program, right? Where you have to like figure out injection orbits and stuff like that. And you can play with different amounts of thrust for a spacecraft and see where it goes. Maybe that kind of thing would be possible.
Would it be too simple to make something like a pork chop plot generator?
Ooh, that's a good question. It depends what the PIC32 is doing. If you're doing all the calculation on the lab PC and then, as long as the rendering is sufficiently involved, then it's fine. Yeah, then it's fine. Do lattice Boltzmann simulations. These are kind of cool. You could do, ooh, these are cool. I don't know if this is kind of half physics, half something else maybe. Diffusion limited aggregation. In the playlist that is Bruce's 2017 lectures for this course, if you scroll to the bottom of that playlist, Bruce has an example of a diffusion limited aggregation simulation running. This is the process by which things like ice crystallization behaves in a way that's kind of like this. So if you go out to your car in the morning, or if you look at your window in the morning, and there's sort of the tendril-like crystalline structures that have formed, it's kind of a diffusion limited aggregation process where there's particles floating around, and if they encounter particles that are already adhered to some surface, then they stick, and you end up forming these very interesting looking tendril-like structures through this process. Good for real-time display on the TFT.
One thing that's fun to do with the diffusion limited aggregation is to start out with a seed which is recognizable like text, and then grow curlicues on it using DLA. That's pretty fun.
Something I love playing with are these diffusion reaction systems. So this would be numeric integration of two coupled differential equations and then visualization of the output on the TFT display. And the coupled differential equations that you're integrating describe the diffusion and reaction of two chemicals with random initial placements on some surface. So you have a clump of chemical here, a clump of chemical here, and it's all on top of some other chemical. And when you click go on the simulation, these start to diffuse, so they sort of smush out. And then as they smush out, they're also reacting with the other chemical that's present to create chemical that doesn't react. And depending how you place these initial configurations and depending on the knobs that you turn in the parameter settings, you end up forming animal spots, animal patterns. This was a contribution from Alan Turing, of all people. I think he has a famous paper that I think is called something cheeky like How the Tiger Got His Stripes or something like this. But it describes how these diffusion reaction equations and systems, this is the mechanism by which things like giraffe patterns and leopard spots and cheetah spots and tiger stripes. It's the mechanism by which these things are formed. And if you build yourself a sandbox for playing with these equations, and play with the parameters, you can generate patterns for creatures that don't exist, and then you turn the knob a little bit more and you go, oh my God, that's a leopard. And so it's interesting because all of a sudden just organic stuff pops out of this simulation at you, which is very addicting. It's a really fun thing. Once you get the sandbox built, it's a very fun one to play with. What else? Here's one. A favorite of mine. How about the Mandelbrot set? I don't know about the Mandelbrot set. This is another lab that we do in the 5760 course, is real-time visualization, zooming, and panning of the Mandelbrot set. The Mandelbrot set being a fractal structure who, even if you don't recognize the name, I'm sure you'll recognize the image. This, right? Very famous fractal, probably the most famous fractal, with the unbelievable property that the edge of this structure is infinitely rough. So what that means is you can zoom in on the edge of this structure forever, and you will keep finding more structure and different structure. It's a non-self-similar fractal, which means as you zoom down, you keep finding stuff and you find new stuff as you go. It doesn't start to repeat itself. You can generate the Mandelbrot set by running a shockingly simple iteration. So the project here would be, you would consider the TFT display screen as each pixel on that screen would be a particular coordinate on the complex plane. So real part, imaginary part. So each pixel becomes a coordinate. You run this iteration on each pixel. And if the iteration diverges after a certain number of calculations, then you say, okay, this is outside the Mandelbrot set, and you color it one color. And if you run a certain amount of iterations and it's still finite, in fact, if it's still less than 2 is the trick, then you say, okay, I'm going to assume that's in the Mandelbrot set, and you color it a different color. If you do that for every pixel and you look at what you end up drawing, it's this picture here. You end up drawing the Mandelbrot set. How fast could you do that on the PIC32? I don't have a good answer for that.
This would be an interesting exercise in arithmetic optimization. I think there's lots of room here for figuring out how to do complex arithmetic cheaply.
And then you could consider building a simple interface that allows for the user to select a place on the edge and start zooming in. So you'd zoom in, recalculate, zoom in, recalculate, down as far as your precision will allow for you to go, which will probably be a few levels deep, enough to see some structure. And there are some cool places to look in this. This is a famous enough fractal that has been sufficiently explored that there are parts of it that now have names. So Seahorse Valley is the area between this main cardioid here and this first bulb, this valley. If you zoom in on that valley, you end up finding these structures, which look kind of like seahorses. So it's called Seahorse Valley. There are other parts of this set with other famous names. So you can build yourself a tool for exploring it, which is highly addicting, like a lot of these projects. Okay. Any other physics or sort of simulation-based projects that people are thinking about? Okay.
Not exactly physics-based, but another game-based project, which I don't know if it's feasible because there will be a lot of latency. What I was thinking is that we can have a few balls jumping around on the TFT. And what we can do is we can use the camera to open up the screen. Then we can use OpenCV from Python and, map the screen that we are seeing to the TFT, and like every click that we have will give us a coordinate on the TFT, and we can just send the data from Python to PIC, and maybe we can do something about it. But the bottleneck will be the camera latency.
So you're proposing sending camera data into the PIC and rendering what the camera is seeing on the TFT display?
Not exactly the camera data. What we can do with OpenCV is that we can read the screen that we are seeing on the desktop, and from there we can, sort of get the values of the coordinates on the screen that we are clicking, and we can map those values from the screen to the TFT. So it will be basically like we are clicking on the TFT.
Okay, I see. Yeah, that could be good. So essentially giving yourself a mouse capability to the TFT,
Right,
something
right,
approximately.
right.
Okay. Yeah, that could be interesting, particularly if coupled with a game or something like that.
Mhm.
That could be very interesting.
Yep.
Music and audio, I'm going to skip over just for the time being because we've talked quite a bit about that. Robotics is a tricky category because we're not in the lab. So the only real roboticsy sorts of projects that occur to me are the ones that use the pan tilt servo assembly that we're going to be using in lab 4. So you might do something like you could play music into the PIC and do like beat extraction and make your robot dance in a way that makes sense with the music. Maybe. So music, beat extraction, and dancing. Maybe you can come up with some other stuff that uses that pan tilt servo assembly in clever ways. That's just something that occurs to me. Skip over historical interest for just a second. With regard to lab infrastructure, what I'm talking about here is you could do something like you have the audio output of the lab PC going into an analog to digital converter on the PIC32. So you could make something like a TFT displayed oscilloscope, right? That samples the ADC at some rate and then shows the waveforms on the TFT display and allow the user to do things like set range, set range in both the X and Y directions, both the voltage and the time dimensions, set the trigger value, set the trigger settings, that kind of stuff. So you could make a small PIC32 oscilloscope. Might be kind of fun for people that are interested in infrastructure sorts of projects. Historical interest, I'm thinking of like retrocomputing sorts of things. So if you are interested in the history of computers and of computing, it is sometimes the case that you can build emulators of old systems on modern systems. I don't have great examples of this, but you might be able to do some research and find some stuff that's feasible. The only thing in this general category that I've done on the PIC32 is, and it barely fits the category of a computer really, is an Enigma machine, which is the World War II enciphering device that was used by Axis powers to encode their messages. And it's a cool electromechanical device that's not too difficult to emulate on the PIC32. But stuff like that, if there's a particular aspect of some piece of history technologically that you are very fascinated with, you might be able to figure out a way to emulate or understand that piece of history by building it on the PIC32.
For instance, could you bring up the original Apple II operating system by emulating a 6502? Could you, there is one of the first interactive lab programs ran on a PDP-8 with 4K of memory. And it had a stripped down version of Fortran on it called Focal, F-O-C-A-L. I'm sure that would run. If you could emulate the PDP-8, you could run Focal on the PIC32 for a twisted language environment.
And then I'm going to add some things to the music and audio section. Many of these things we've sort of discussed in the past, but instrument synthesis is a wonderful category of project. So stringed, etc. Stringed instrument synthesis, make violins, make pianos, make that sort of thing. General synthesizers of all sorts of sounds. So you can make the old school sci-fi laser pew pew sounds, and you could also make bird calls and whatever else, right? So just the general category of synthesizing sound of any variety. So bird calls, sound effects, instruments, etc. You might consider doing note identification. You sing to your pick. Your pick figures out the frequency that you're singing and tells you, that's a A flat or whatever it is. That's a project that works really well. Play a flute into the pick and it'll tell you the sound that you're playing. You might even have it, we've had projects in the past where people play into the pick and it writes the music out for you in notes. Some infrastructure involved in doing that you'd have to think about, but you could do something like that. You could do voice compression. You talk to the pick, filter your voice into, you do essentially a FFT of your voice in a bunch of different bins in frequency space and figure out how much power is being put into each range of frequencies in my voice. Then use direct digital synthesis to additively combine sine waves with amplitudes directly correlated with the amount of power in each of those bins, and you can create very robotic sing-songy versions of your voice. Kind of cool. Voice compression and auto tuning, I will say. Spectrogram drawings. Another YouTube rabbit hole you can go down if you want to. Can you come up with sounds that will create images in your spectrogram? Draw smiley faces in the spectrogram. Or more complex things. People have drawn, if you go on YouTube, my God, people have done some wild things. Head transfer functions. Synthesize slightly different sounds to each of my earbuds so that I think you're sending, that I am listening to something that is behind me, or to the right of me, or to the left of me. Or create a sound, maybe the sound of a bee buzzing, and make it sound like it's flying around my head. Those are pretty cool. Here's an annoying one. How about a Zoom jammer? So you talk to the pick, it hears your voice, processes it, and sends your voice back into the Zoom call so that you have to listen to a slightly delayed version of your voice as you speak. You can try this online. It completely screws up your brain. You can't talk anymore. You could create a system that does that in Zoom that completely jams a call, that makes it impossible to talk anymore unless you mute that thing. We're out of time. I can make this document available to people if they want to keep thinking about some of these categories or play with any of these ideas. There are lots more. And we could do this again at some point before your project proposals are due, if that would be helpful. But I just want to get people sort of going and thinking along these lines. Any questions?